This is a standing wave generator. Instead of a broadband short pulse, we'll excite it with one frequency at a time and let the energy build. The ends of the strings are maintained at a fixed point. At this frequency, the string is half a wavelength long. A wave traveling from the center and reflecting from the right travels 180 degrees. In that same time, the wave sourced by the generator on the left travels 180 degrees. When the reflection from the right meets with the generated wave from the left, the two signals are 360 degrees apart. They're in phase and add constructively. When the string is 3/4 of a wavelength long, the wave traveling from the center and back again after reflecting off the right travels 270 degrees. And in that same time, the generated wave from the left has traveled 270 degrees. So the two signals are 540 degrees apart, they are out of phase and add destructively. And this is true at every point on that line. When the string is one wavelength long, we can see a full sine wave develop, with the null at the middle. The string is 36 palms long, and the null is at the 18th. When we're at 1 1/4 wavelengths, the generated and reflected waves again are out of phase at every point on the line. Since they're out of phase, the waves cancel each other out. And when we're at 1 1/2 wavelengths, we can see 1 1/2 sine waves develop. We have 4 nulls now, each spaced 12 palms from their neighbors. And we have 3 peaks, again, spaced 12 palms from their neighbors. Now I'm going to show that we can model at what frequency these constructive and destructive interferences happen for a given string. This is Circuit Mason. It's a simulation tool that is typically used for electrical simulations. Microstrip lines, amplifiers, capacitors, that sort of thing. It's easy to add new models in the code, so I've made a mechanical string model and measured the tension, weight, and length of the string from the previous experiment. This code shows what happens over frequency, instead of showing what happens over time like the previous simulations. This is a companion code which can calculate how big the wavelength is on a line for a given frequency. We measured the line to have a tension of 1/2 Newton, the string weighed 3.3 grams, and it was 65 inches long. For the measured data, we predict this line is one wavelength long at 9.6 Hz. Since one wavelength is equal to 360 degrees. Here we have our predicted response over frequency. So at 4.8 Hz, we see a strong response should happen. At 9.6 Hz, we see a strong response will happen. And at 14.4 Hz, we see a strong response will happen. And we also see the nulls that we predicted at 7.2 Hz and at 12 Hz.